Today we're looking at how can we use the equations of uniformly accelerated motion to design a laboratory investigation to determine the acceleration due to gravity. If we were on a block schedule like last year, we might be able to get to all of this today. So today we're going to just take a look at a velocity time graph and getting these equations. Once we get the equation that we need at the end of all this, I'll explain how we use that equation to do some lab work, and I will save that lab work for probably another day. I don't know if I have time to get to it. So I would suggest constructing, this in your journal, and as we go through it, if you need to stop me if you have questions about anything, please don't hesitate to ask. We have an object that starts at a non-zero velocity and uniformly increases its velocity to a faster, speed. So one of the things that we can do is take the slope of this line. Okay, and when we do, we're rising in meters per second and we're running in seconds. And so the units give you a big clue as to what you're figuring out when you take the slope of a graph. Meters per second, meters per second squared, those are the units of acceleration. So on this axis, we're changing our velocity. We're going from some initial speed, we're going to call it u, to some final speed that we're going to call v. This is just me labeling this axis here, but to just make it a bit more tidy, I'm going to kind of get rid of it right now. Oh, that makes it tidy, right? There, just like it never was. All right. I'll label it up here. Velocity in meters per second, right? So I'm going from some speed v to some speed u initial to some speed v final. Okay, from the chalkboard the other day, that's how we described or defined these variables. And that's happening if this is time 0, then let's say that occurs over time. Let's be creative. Let's call it that happens in time t. We call it t for time. All right, so an object that speeds up over time t. I think that's what we've got. Acceleration is the change in the velocity. So from v to u, right? It's a difference in velocity over the change in time. So in general, acceleration is the rate of change of velocity, the change in velocity over the change in time. The way that we're writing these variables, it's u for initial velocity, u for initial. Or you can think about it comes first alphabetically, like TUV. So u is before v, so that's why it's initial. That probably makes more sense. Oh, it's u for initial velocity. All right, so we've got this. Acceleration is the change in velocity over time. This time, 0, like this time is t. I should have made a capital T to be consistent. That's the time to this up a little bit here. If time right here is 0, it's like t minus 0. Well, minus 0 just stays as t, right? So we'll just leave it like that. One of the things we don't like with our equations of motion, our equations of uniformly accelerated motion, are the things that you don't like as students of math, like fractions, negative signs, no good, right? So let's get rid of all that. I'm going to multiply both sides. So if a equals this, I'm going to multiply both sides by t. All right, so I'm going to get this as, let's rewrite it over here. AT, right, multiplying both sides by t is v minus u. Remember that. V minus u is AT. Okay? To get rid of this negative u, add u to both sides. There you go. There you are right there. So we've got our equation v equals u plus AT. We'll call that bad boy equation 1. Note that equation 1 relates the initial velocity, the final velocity, the acceleration, and the time. It doesn't include anything about displacement. And it's just based on the definition of acceleration itself. Right? Acceleration is the rate of change of velocity, and if you just sort of take that definition over, there you've got it without any fractions or negative signs. So that's equation 1. The slope of a velocity time graph gives acceleration. That's all that we've done here. The other key idea is that the area underneath this curve gives displacement. And again, the units are a big clue. If we rise, when we're doing slope, we rise in meters per second, right? The units of the numerator here are meters per second. The units of time are seconds. So rise over run, we get meters per second, or what are the units of acceleration? Meters per second squared. We get those units when we take the slope. So it gives you a clue about like, okay, yeah, that's correct. You would expect those units for acceleration. What about if we take the area underneath the curve? Like what is the area underneath this? I guess this shape would be technically a trapezoid. Like you know the area of a trapezoid, you can use that formula. I prefer to break it down into a rectangle and a triangle and just add them up. Okay. So an area problem is like we've got, let's start with this here rectangle. If we just maintained a constant speed of u over time t, then this is how we talked about yesterday. Then we just cover a distance that would be equal to our speed times our time, right? So the area of this rectangle here gives the displacement. Use S for displacement. Maybe I'll see that.
Yes.
Thank you. I'll ignore it for a bit. Important enough that all that. But who knows they're being checked out? It's like, no, that's not taken out of here. Just go. You know, okay. All right. It's like a. All right. So S equals UT. Okay. Remember that this U is a velocity, so it's like just velocity times time gives the displacement. There's no acceleration here. This is just if this is the displacement from this part of the graph. Okay. Again, the units give you a big clue. Meters per second times seconds. The seconds cancel, and we have meters of displacement. Okay. What about this added part right here, the triangle? A triangle has a area formula, 1/2 base times height. So we're going to say here's some more displacement. If you're accelerating, okay, speeding up, you don't just cover the distance you would, you know, if you were going at constant velocity, you cover some more distance. Okay, like there's some added distance that we're going to cover by virtue of the fact that we're speeding up this whole time. This is just the displacement because we started at that speed. Okay, so we need to factor in this. So we've got more displacement, S, going to be equal to 1/2 base times height, right? So 1/2. What's the base of this triangle right here? It's the difference between V and U, right? So it's V minus U. That's this height right here. So that's V minus U. What is V minus U? V minus U equals, anybody remember? AT. Okay? V minus U equals AT. That's when we multiply both sides of this by T. So this base right here, I will put in blue chalk. That's equal to AT. So if I'm writing an equation for the displacement represented by this triangular part of the graph, 1/2 base times the height, right? The height of this is still t. 1/2 AT times t, so that's 1/2 AT squared. So what's a good equation that solves for the displacement of something that's undergoing uniform acceleration? Displacement equals UT, that's the displacement by virtue of the fact it was already going some non-zero speed, U, plus a 1/2 AT squared. That's the displacement represented by this part of the graph, okay, from the accelerated part of the motion. So the total displacement that an object undergoing uniform acceleration covers is UT plus 1/2 AT squared. And that, sure enough, is equation 2. This is the one that we're going to use to answer this question. Okay, we're going to come back to equation 2 and say we can get a lab out of that. We're going to use this to figure out the acceleration due to gravity. Okay. And I don't want to make the lab more complicated, so we're going to choose an initial velocity of 0. So we're just going to get rid of that term right there, right? The initial speed is 0. Now in this one, it's not, right? Like there is a non-zero initial speed. This is like you're going 35 miles per hour and you're merging onto the highway, so you got to speed up. And an engineer might say, how big do I need to build this on-ramp to the highway? What are the speeds that are going here? What's the area underneath that curve? What's the displacement that I need to factor in? So remember, there's a practical importance of this physics. You know, this is actually how far something's going to travel. It goes from a speed like this. This is very general right now, right? And abstract, just general variables. So you can plug in actual, numbers, and that's the benefit of this, is that these equations are very general and they solve for lots of different things. Every equation is missing one of the 5 variables, okay? In the big 4 equations of uniformly accelerated motion, you relate initial velocity, final velocity, acceleration, time, and displacement. Let's do that. Displacement, initial, final, acceleration, time. So there's 5 variables related in the big 4. Each equation will omit one of them. Note that there's no displacement in this. Note that there's no final velocity in this. So you have to, when you're solving problems using this kind of physics, you say, what do I want to know? What do I know? What can I solve for? Which equation is helpful in solving this? So far, we've got 2 of them. We've got 2 more to go. All right. Now, at this point, I might want to redraw this to make it a bit more clear. So I'm going to go over. I'm just going to reconstruct this kind of a plot down here. Is that okay? You two, you still see that okay? Great. We've got velocity, meters per second, time, seconds, and we want something like this. U to V. In time. All right, here's the next thing we can do. And again, in your journal, you might want to do the same thing. Like, okay, I've got enough. I got 2 equations out of that one. Let me draw a clean one. You don't want to, if you do all the working on one, it's going to get pretty cluttered. What we're going to do is consider the average value between U and V. Okay, so if we started at speed U, we ended at speed V, the average is going to be kind of right here, right? Like that. Does anybody know mathematically what that is, what value it has based on these variables? V plus U, or U plus V, over 2, right? It's their average. So you add them up and divide by 2. So if this is value U, this has a value of V, the value between them is V plus U over 2. Okay, so that's the value of this dashed yellow line. What's the area underneath that dashed yellow line? Well, first, what's an area of a velocity time graph going to give you? Displacement. We just did it over here, right? We took the area underneath this curve. Instead of taking the area of this trapezoid now, we're going to say, can't we just make it a rectangle? Like just make it an average between these two. That's simpler, right? So here we're going to still solve for displacement because we're taking an area, and we got length times width. Okay, so let's see what that's going to be. The displacement is the area underneath the curve, and the area underneath this curve, straight line. All right, so we've got, I'm going to rewrite this slightly. I want to see if you're okay with this. 1/2 U plus V. 1/2 U plus V, same thing as V plus U over 2, right? I can factor out a 1/2. So that's the length of this rectangle. The width is still T. So I have 1/2 U plus V, length times the width, which is T. And that right there is the width. Note that these are the big 4 equations of constant accelerated motion, and that one doesn't have acceleration in it, right? So this equation omits this variable, A. Because we kind of did away with it, we said, yeah, I know we accelerated from U to V, but on average, we were just going this constant speed, V plus U over 2, right? Like, so that's just a constant average speed that we were traveling, okay? And indeed, the area underneath it will give you the correct displacement. In other words, you could use this equation or this equation to solve for displacement. It just depends on like, what do I already know? If you don't know the acceleration, but you do know u and v, use that one. It's kind of like we didn't count this area, right? Like we didn't actually travel this, right? Like that's our actual motion. So it's like, oh, you're missing this area, but look what we did, you know, it's like that and that, not the way I drew it. But those are the same, right? And so by just sort of averaging it out, you're missing out on that, or you're taking that out, and they're equal. So it works. And now comes time for equation 4. All right, equation 4 is going to be the one that doesn't have time in it. So see how all of these have time so far? So we want an equation that just relates everything else besides time. So we want to eliminate it. Let's see what we can do for that. Let's go back to our very first one, which was, you know, v equals u plus at, or remember that came from like a equals v minus u over t. Let's rewrite that to make time the subject. What is t in terms of these variables here in equation 1? Take a minute to figure that out for yourself. I'll do it right over here. If a equals v minus u over t, sometimes this is a great way to think about, you know, calculating. You don't always have to say, well, the way I wrote equation 1 is like that. Sometimes it makes sense to like plug in values here and solve for acceleration, right? Instead of like doing the algebraic manipulation on like what you've got memorized, you know, it's the same thing. So I'm going to do the old algebra switcheroo there. T equals v minus u over a. Can you teach you that now? Algebra switcheroo. Those can just change spots. Well, I'm multiplying both sides by t and dividing both sides by a, right? They do teach you that in algebra. So that's what t is. It's v minus u over a. Okay? That's what t is. S equals. Instead of writing it like this, I'm going to write it back like this way. U plus v over 2, right? So I'm just basically taking the same equation 3. I've got that. Got to multiply it by t. What is t? V minus u over a, right? So I'm substituting in these variables, which I know are equal to t, right? I'm eliminating t from that equation. So what is t? T is v minus u over a. U plus v over 2 times t. But instead of writing t, I'm going to write what it's equal to. V minus u over a. All right. We got to multiply these two now. Our favorite. I'll do the denominator. You guys take care of the numerator. That's fair. 2 times a is 2a. You're welcome. Now you guys do the numerator. We gotta do what here? Gotta distribute. Some of you might be saying, I gotta FOIL that. I gotta FOIL these binomials here. But that math is coming back to help you, not harm you, right? U times v is uv. But the middle term's going to cancel, right? Because we do negative u times v. Okay. So let's just write it all out. Let's just distribute. U times v is uv. U times negative u is negative u squared. V times v is v squared. V times negative u is negative uv, right? I just FOILed that, or distributed, it's the same thing, like the order that you do it in. And then I'm left with what? uv minus uv is 0, so those go away. Negative uv and this uv would cancel, right? So I just have v squared minus u squared, or negative u squared plus v squared, however you want to write that. Let me rewrite it like this. S equals v squared minus u squared over 2a. Just like up here, we don't want negative signs, we don't want fractions. Let's clean it up. Multiply both sides by 2a. Add u squared to both sides. And you get, I wish I just had a little bit extra chalkboard down here, right? To just finish it off. 1, 2, 3, and 4 right there. I ran out of room. Go back over here, maybe. I guess that's the best we can do. Sorry, guys. Equation 4 then is going to be, let's write it nice and clean. B squared equals u squared plus 2as. Everybody good from that step to this step? Just multiplying both sides by 2a, then adding u squared to both sides. And we should get equation 4 as the final velocity squared will equal the initial velocity squared plus 2 times the acceleration times the displacement. So no time in that one, but it relates all the other 4 variables. We're going to use equation 2 to determine the acceleration due to gravity by thinking through an experiment now. Okay, so let's take some time to do that. Although, I think if I were to do this working over on the whiteboard, because I'm projecting this right now, it will create an infinite parallel universe. Or maybe Agent Carter is Captain America. I don't know. Question? All right. This is going to be called the drop ladder. Why drop? Because remember, I don't want any initial velocity. If you drop something, what's the initial velocity of the thing you drop? Exactly, right? So the initial velocity is 0, so that term goes away. I don't care what the time is, if u is 0, that term goes away. It's not the throwdown lab. One, that sounds, like threatening, but this is the throwdown lab. You just throw something down. No, just drop it. It's a drop lab. The math is way tougher if you're throwing down. Okay, it's not a throwdown lab, it's a drop lab. So then it becomes the displacement equals 1/2 at squared. So let's just be complete here and say, okay, we're starting with displacement equals ut plus 1/2 at squared. We want to get a lab out of this so we can figure out the acceleration due to gravity. You see that okay, YouTube? Leave it down in the comments below. That's probably a good time if you're not already on the Dr. Site notification slide. Turn your phone sideways and make that red button gray, right? That's what you want. Subscribe, make sure you like, leave a comment down. All right, this term goes away because we're dropping stuff, so the initial velocity is going to be 0. So we're going to rewrite this as s equals 1/2 at squared. Already better, right? Already friendlier to work with. The displacements are going to be heights because we're going to be dropping things. So instead of calling it just S for some general displacement, I'm going to call it height H. Okay, H for height. A type of displacement, like a vertical displacement of height. Okay. So H equals 1/2. Now I say the acceleration due to gravity times time squared. When we're dropping things in Earth's gravity field, we can call it the acceleration due to gravity with a subscript. Oftentimes, we're just going to call that lowercase g. We just kind of drop the variable a. If you look up here, you can see on that poster, right, F equals ma, but W equals mg, sort of right there. Okay, so g is the acceleration due to gravity, called local g. All right. So I'm just going to write this as h equals 1/2 gt squared. And I would say this is a very useful shortcut equation to keep in mind. It comes from this more general equation, but like you're trying to relate how much time it's going to take something to fall on Earth, that's the equation you got. How high up is it? What's Earth's gravity field? How much time is it going to take? It goes as the square of the number. So how can we get a lab out of this where we're going to deduce G? We're going to vary the height that we're going to drop things, and we're going to time how much time it takes to hit the ground. Okay. So our data table is going to look something like measure height in meters, drop things, time how long they take to hit the ground in seconds. So that's the data that we're going to collect, independent variable, dependent variable. Everybody should agree that the higher up we hold things, the more time it's going to take them to hit the ground. That will be true without exception. But we really want to know t squared. Okay, that's what we actually want to know because we're going to graph y equals mx. Okay, so the goal here is to take our equation, h equals 1/2 g t squared, and think about it like a line. I could plot all my heights on the y-axis, the vertical axis. I could plot all of my time squared values, calculated values, right? I can't measure this directly. I can't measure time squared. I can measure time, and I can square it in my calculator, right? And plot these numbers on the x-axis. And then my slope of my best fit line should be equal to 1/2 g. So I can actually use my graph to determine the slope. How does this quantity sort of relate to that quantity? Determine the slope, the numerical answer, what is the number that this is equal to, and just set it equal to 1/2 g. So the final step in your analysis, after you've plotted all this data, drawn your best fit line, found the slope of it, is setting that slope equal to 1/2 g, and then solve for g. So your conclusion will be g equals something. And if you think about the graph that we're making, right, we're plotting height in meters against time squared in seconds squared. When we take the slope, the rise over the run, meters per second squared. So our units are going to be the correct units of acceleration. Meters per second squared of acceleration. Okay. So we're going to do this lab, maybe tomorrow. We'll do it perhaps together as a class, and we'll use photo gate timers so that we can time that very accurately. Maybe a handful of students that have me for astronomy, we sort of do this with stopwatches, and you can get a pretty sort of accurate answer with that too. But this is actually where the sort of theory behind that comes from. This is how we can use this equation. Sometimes it's just given, like, this is how gravity works, but like, well, why? Because we can prove that all those equations sort of just fall out of these ideas of the area underneath gives displacement, the slope gives acceleration, all right? So that'll be the drop lab.